The topic of this video is covariance and correlation, and this is section 1.5.6 of Wessel's notes. Now remember, the quantity we use to measure the spread of our data or variation within our data was the variance, and that was denoted S squared for a data set X, and that was the sum over all our data points of the deviation of X of each data point from the mean squared all over the number of degrees of freedom, which is the number of data points minus 1. And the 1 is for the one derived quantity, which is the mean. But oftentimes our data involves two or more variables. And we're often interested in understanding the relationship between those quantities for learning about the Earth, learning about the natural processes we're studying. So let's, for example, if we have, we collect data and we measure a quantity X as well as a quantity Y, we could also describe the spread of Y as the variance of Y. Just as we did for X, right? And to examine how the two vary together, we would use the covariance. And the covariance will denote as S, X, Y. And that's equal to, again, we're summing over our n data points. And we're looking at the deviation of X from its mean times the deviation of Y from its mean. And then divided by the number of degrees of freedom. So let's, for example, X could be say water well temperature. And in the data set, some of you looked at in our first homework assignment, what was the range? The range was somewhere between something like, what was it, 18 degrees to something like 80 degrees C. And Y, for example, could be, say, depth of the water temperature measured. And that varied between, what was it, something like, 10 feet to something like 8, what was it? Say, well, let's just say 1,000 feet. I don't remember the range of the data set that we looked at, but let's just say the range is 1,000 feet in this example. And you'll notice X and Y have different units and they span a very different range. So it would be smart when we want to quantify the covariance between X and Y to normalize the covariance. And so we would do that. Let's see, let's normalize S, X, Y. And a smart way to normalize it would be by the standard deviation of X times the standard deviation of y. Okay, so that and that gives R, and that's the Pearson's linear correlation coefficient. Or just correlation coefficient for short. And let me go ahead and write that out. R is equal to the sum over our data points of the deviation of x from its mean times the deviation of y from its mean all over n minus 1. And that is divided by and that's all over n minus 1 as well. So let me continue on the next slide with that written out. And so R ranges from -1 to +1. And if the absolute value of R is close to 1, then that means X and Y are strongly coupled to each other or related to each other in a linear sense. Okay? And if R is close to 0, then that means X and Y are not strongly coupled in a linear sense. So on page 26, Wessel shows whatever 6 sort of plots of X versus Y, some example data sets, and he shows different correlation coefficients for them. Some of them are positive when the X and Y show sort of a positive linear correlation. Some of them are negative when X and Y show a negative correlation, and some of them are very, very small. But let's look at an example. And let's look at a very simple example so we can make this really intuitive for everyone. So I'm going to draw 2 axes, an X and a Y axis. And let's consider a case in which we have n equals 3 data points, and X and Y lie perfectly along a line. Okay, and this is a really simple example. So X and Y go between -1 and plus 1. In this really simple example. Okay, so in this case, Sx equals 1. The standard deviation of x is equal to 1. The standard deviation of y is also equal to 1. And therefore, if we let's look at r. R is equal, again, to the sum over 3 values. So it's the product of the deviation of x and y from the mean. And that gives, heck, I'll go ahead and write it out. I equals 1 to 3 of xi minus x bar, yi minus y bar all over n minus 1. And x bar and y bar are both 0, right? And so we get, as the sum, we get, if we start from this left point, x is minus 1 from its mean value, and y is also minus 1 from its mean value, and then we have a 0 for both values being at 0, and then this upper right point gives us a, gives us a 1 times a 1. And that's divided by 3 minus 1 is 2. And so r is equal to 1 plus 1. So let's look at another case in which we also, again, we have 3 data points. And in this case, they they vary along a line that has the opposite slope. So let me draw the line in which they lie along. Okay. And in that case, r will be, starting from this point, we'll have a minus 1 for the variation of x from its mean, and a plus 1 for the variation of y from its mean, plus a 0, and then we have a 1 and then a minus 1 divided by 2. And in that case, r is equal to minus 1. And then the last example, let's consider if x and y are coupled to each other, right? But they're coupled along a circle. So we'll have, so let's just add, I guess, 4 more points to our data set. We'll keep the blue and the green data points, but we're just going to add some more data points. And in that case, we get r is equal to plus 1, and that's for the green data points that we looked at. And the blue data points give us the minus 1. And then these red data points on the axes give us a 0, right? Because either x or y is 0. And that gives us a correlation coefficient of 0. So here's an example in which x and y are clearly related to each other, but not in a linear sense. So we get a 0 correlation coefficient.